Welcome to Algebra 2. I wanted to be clear that before we start studying algebra, which you might remember from Algebra 1, involves something to do with solving things or simplifying things or evaluating things. You might remember some stuff from algebra, maybe you don't at all. But either way, I thought it'd be worthwhile before we start diving into Algebra 2 that we spend some time trying to figure out why we're even learning algebra in the first place. And to understand that, we need to go back another step and understand what a function is. And so, what's being demonstrated on this slide is essentially this idea that functions are things that happen all around us. And what mathematics does and what algebra does is it presents a way, a language, that'll enable us to talk about these functions, these things that happen around us. So, for example, mathematicians and scientists will utilize functions to produce a beautiful fountain display just like this. And physicists will use functions so that they can develop a roller coaster that will stay on the tracks. And this is what's called a fractal, which is an example of a special type of function, and it produces a pattern that is quite mystifying if you start to dig in deep. Of course, there's also functions when we think about the functions of the body, the circular system or the digestive system or whatever. This graph could be anything, but it oftentimes represents things like population growth or government spending over time, whatever you want to call it. So needless to say, functions are things that happen all around us. So we need to know what a function is, and we need to learn how to use the language of functions to help us study algebra better. Before we do that, before we even study what a function is, we need to understand the meaning of a word variable. So you guys know what a variable is. In fact, if I asked students what a variable is, they would probably say something like, it's x. But more importantly, in real world, a variable is usually a quantity, a number system that can change. And what we do when we study functions is we pair two different variables or two different number sets against one another. So there's going to be an independent variable, and there's going to be a dependent variable. And we're going to basically, when we study functions, we're interested in how does change in the independent variable affect change in the dependent variable. Now that's all kind of abstract. So if you want to understand independent variable better, think about a scientific experiment. The independent variable is going to be the variable that a scientist is going to allow to change on its own or to change themselves. The dependent variable then changes as a result of a change in the independent variable. So in other words, the dependent variable changes because the independent variable changed. Again, abstract, kind of confusing. Let's put it in for examples. A scientist is testing the effect of light and dark on the behavior of moths. He does so or she does so by turning a light on and off. In this case, the independent variable is the amount of light, and the moth's reaction represents the dependent variable. So the moth's reaction to light will change depending on the amount of light that they have. Here's another example. You study diamonds. People that tend to get wealthy, they tend to like to buy diamonds as an investment. And it turns out that there are variables in diamonds, for example, the size and the quality. Let's focus on the quality. The quality of a diamond we will call the independent variable, because it's the quality, whenever the quality of a diamond improves, the value of the diamond improves as well. So if quality goes up, value goes up as well. So the value depends on the quality of the diamond. The third example, suppose you're interested in average high temperatures in Wisconsin. You should know that the high temperatures will change depending on the day of the year. So every day of the year is represented by the independent variable. Since the high temperature for the day depends on what day of the year it is, the other variable, temperature, will be the dependent variable. So temperature is dependent and the time of the year is independent. So one has an effect on the other. Changing one will have an effect on the other. So that's the nature of functions. So, moving forward. Here, this is an example of a story that I heard on the news. Actually, I read this on the Facebook or something like that. Somebody did a study about pizza size versus the price. So this is an example of a function that many of us, myself included, especially given my size, can relate to. And basically what somebody did was they went to a bunch of pizza restaurants all over the country and compared the diameter, that is how big across a pizza is, against the price per square inch. So that's how much are you paying for each bite of pizza, basically. And what this scientist discovered was, as we increase the diameter of a pizza, the price per square inch of that pizza goes down. In other words, for an 8-inch pizza, you're paying hold on. Basically, if you got a 20-inch pizza and you would have to spend $20.77 on average. That's the average price of a 20-inch pizza. If you want to get the same amount of pizza by area and buy it in 14-inch varieties, you would have to spend $30 almost, so almost $10 more. If you want the same amount of pizza, except you're going to get a whole bunch of little 8-inch pizzas, you'd have to spend on average about $51.56 on pizzas to get the same amount of pizza that you get from a regular 20-inch. So it is through the study of functions that we are able to observe patterns, and it is through our understanding of patterns that we're able to make conclusions about how to spend our money, for example. So here you can actually see a graph of a function, and then you can see another a diagram that sort of gives you a better sense of what the graph is trying to tell you. And of course, there's a pizza. All right, so here's an activity that I would like you to do today, right after you get done watching this video. What I've presented is a list of some potential function relationships. And so, for example, there is the idea about the heavier the envelope, the more expensive the postage cost. And here's another one: as a radius of a circle gets bigger, so does the area. And so here we see there's this thing about the weight of an envelope, and we see the cost of postage. And here we see the radius of a circle, and then we see the surface area of the circle. And they're related to each other, and it is in fact a function relationship. What I'm going to ask you to do is to translate this function relationship into the language of functions in particular. So what I want to do is first talk to you about the language of functions, and then I'll demonstrate how you're going to do this little mini assignment. So an example of a function is hair length. Hair length is a function because there's only one hair length for every moment in time since your last haircut. And then the big idea here is haircut or hair length is a function of time because... Actually, let me start over on that sentence. Sorry. What we're going to do is, again, we're basically saying, what I'm basically trying to get across here is you can establish a function relationship in just about anything. And one example is hair length. How long your hair is depends on how long it's been since you've had a haircut. Now, if I got a buzz cut, my hair would be really short. But if I got a buzz cut 2 years ago, my hair would be really long. So basically, again, hair length depends on how long it's been since I've had a cut. But here's what we say in mathematics. We say hair length is a function of the length of time since you've had a haircut. So is a function of is essentially the math language that says depends on. Your hair length depends on the length of time since your last haircut. Is a function of, depends on. Here's another one. Talking about earlier, I mentioned that the temperature depends on the day of the year. We're going to say it in function language as the average high temperature is a function of the day of the year. And when I mentioned the diamonds earlier, basically we can say the price of a diamond is a function of its weight in carats. Here's an important thing to notice. The weight in carats is the thing that, or in this case, is the thing that determines the price of the diamond. So the weight is the independent variable. The price depends on the weight. The temperature depends on the time of the year. So we got the day of the year is the second part of the statement. That's the independent variable. The thing that you're focused on is the first part of the statement. That's the dependent variable. So to sort of give you an example of what I'd like you to do, I did the first two for you. Here I say the heavier envelope, the more expensive the postage cost. That's a truism, and it's a function in our own day-to-day lives for those of you that still send mail. To change this into math language, I rewrote the statement as you see here. It says the cost of postage, so that's one variable, the cost of postage, is a function of, and that phrase right there means depends on, so the cost of postage depends on the weight of the envelope. From this statement, I learned the weight of the envelope is the independent variable. If I change the weight, that will have an effect on the cost of postage. Here's another one. As the radius of a circle gets bigger, so does the area. Here, I'm going to say that the area of the circle depends on, or is a function of, so depends on the radius. So the radius is what changes. That will make a change in the area of the circle. The area is dependent and the radius is independent. So what you need to do is take the remaining 5 statements, translate into function language, and then identify the independent and dependent variables. If you need to review again, you can rewind this video and look at the examples that I put here, or you can rewind and freeze frame and read some of the examples that are shown here. But basically, it's okay if you're wrong, but I need everybody to make an attempt to translate this language, the blue language, sorry, into the black language. So basically we want normal day-to-day speak translated into math language using the phrase is a function of. Remember, is a function of means depends on. All right, thanks for listening.